So for today, what I want to talk about, now that we've actually learned a method to do hypothesis testing, I want to have a conversation about the things you need to look out for when you're doing hypothesis testing. And I want to focus on that 5%, right? That 5% of error that we're going to have because we're dealing with probability. And what we'll do is we'll talk a little bit about the types of errors that can be made, but we're also going to focus on how to be aware of those and then maybe even fix it. So just a reminder, right? When we're doing hypothesis testing, we're relying on probability theory to decide whether or not we're rejecting the null hypothesis. We always start with the assumption that the null hypothesis is how the world works. Right? So we start with the premise that the null hypothesis is true. Ish. Yeah, let's say that. I'll have to double check, make sure I don't have a test question on that. But let's say we start with the assumption that the null hypothesis is true. We've collected a sample. We've noticed a difference in the sample. And we want to know how likely it is that we would get that sample that shows a difference if the null hypothesis were true. If it's a really low probability, then we can say we're going to reject the null hypothesis, and we've found evidence for our alternative hypothesis, which usually says that there's some sort of difference. But we can do all of the statistics correct and get the wrong answer. Now, hopefully it's a low probability, but nonetheless, we can get the wrong answer. So what I want to talk about today is the situations in which we would sort of do that. So here's an example. We've heard of lie detector test, polygraphs. I'm not going to go too much into it because if any of you ever apply for a job that requires you to have a background check and a polygraph, one of the questions they ask you is, do you know how polygraphs work? So I'm not going to do that, but we've seen enough TV to know that there's this thing called the polygraph. Let's say we hook up 68 suspects to the polygraph, and turns out later that 30 suspects later confessed to the crime. So let's look at sort of what the polygraph outcomes could be. This sort of table is known as a crosstab, which is short for cross-tabulation. So we have two different variables. We have what the polygraph says, and we have what actually happened. So the polygraph can give us two outcomes. The polygraph can say this person committed the crime, this person is guilty, or the polygraph can say this person is not guilty. And so that's why we have two columns, one of not guilty and guilty. The actuality is the truth. Again, there are two truths, two options, and each row reflects that. So in actuality, the person could be innocent, or the person could be guilty of the crime. We have potentially 4 outcomes if we're going to match what the polygraph says to what the truth is. So the polygraph can say that the person is not guilty. And if the person is actually innocent, then good job, polygraph, right? But there are situations in which the polygraph could indicate that the person is guilty when in fact they're innocent. That would be bad, right? That would be really, really bad. If we assume that a person has committed a crime and they haven't, and we kill them, because that's what the death penalty does, that would be, we can agree that would probably be bad. Because a machine said that they did something. Now, I don't want you to think that when you're suspected of murder, we just hook you up to the machine and that's actually what happens, by the way. That's not what happens. Okay. We also could get the correct outcome. Again, the polygraph says that you're guilty, and you are in fact guilty. Yay! We know what happened. That's a good thing. But we could also have the polygraph say you're not guilty when in fact you are guilty. And in that case, the polygraph would miss something, right? And in theory, you've gotten away with a crime. So these are the 4 possible outcomes that we could have. You'll notice that 2 of them are good and 2 of them are bad. So here's the data from the study. Of the 68 outcomes, the polygraph got 15 of them wrong, including a situation in which the person was actually innocent and the polygraph said they were guilty of a crime. We can have the exact same errors when it comes to hypothesis testing. So what we're doing is we're making a decision like that polygraph machine. We're looking at our sample and we're making a decision about what happens in the real world based off of the information from that method. And what we're tasked with doing is determining whether or not we're going to reject the null hypothesis or not. That's how we frame this investigation. Well, we have 2 possible outcomes. We could fail to reject the null hypothesis. Do not reject the null hypothesis. When we do that, we're saying that the world, there's no difference between our 2 groups, for example. Or we could reject the null hypothesis, say that the alternative hypothesis is true. Now, if we reject the null hypothesis, when in fact the null hypothesis is true, we call this a type 1 error. A type 1 error. If we were medical doctors, we would think of this as a false positive. We're saying that there is an effect when in fact there is none. Medically, when you take a test and you're hoping that there is nothing wrong with you, and the test comes back and says, oh, there's something wrong with you, and there is nothing wrong with you, that's a false positive. If you've ever huddled around a pregnancy test, just staring at it, waiting that 5 to 10 long minutes, and you're hoping that you're not. You're hoping that you're not. And then you get a positive. Or we've all seen that movie, right? What happens when you get a first pregnancy test that's a positive? What do? You take another one, right? Because you're hoping, right? You're like, ooh, I didn't plan this. And so you get another one, you take another one, and another one, and another one. And the next thing you know, you drop like $100 on pregnancy tests. And they all say the same thing. Why? Because you're praying that it was a false positive. Right? That's what you're looking for in that instance. Those are bad. Let's go to the bottom half. All right? The alternative hypothesis is true. Well, if we reject the null hypothesis and say that there is an effect, when in fact there is an effect, that's good. We've picked up the thing that we're looking for, that we know, that we thought exists, and then it turns out it does exist. But what if the effect exists and you don't find it? You've missed it. That's a false negative. We call that type 2 error. So you take a test, you're trying to see if you have a condition, the test comes back negative, that's actually a good thing. So anytime there's like a sports injury, they'll be like, this person was taken in for an x-ray, the results were negative. And you're like, yay, that's good. That means they didn't find anything. The results are negative, they're out for the season. Like, it doesn't work that way. Okay? False negatives are bad. Why are they bad? You take a test to see if you have cancer. They're like, no cancer here. What happens to you then? You still have cancer. And then what happens to you? You die because you don't treat the cancer that you have. False negatives are really bad. Now what happens in the social science world? Well, nothing. Nothing bad happens, right? Think to the parking lot study that we did a couple weeks ago. Like, what happens if we fail to reject the null hypothesis that having a stalker matters? Nothing, right? The world continues on. Nothing happens. So we have two types of errors. Type 1 error and type 2 error. Our type 1 error, we actually know a little bit about. Because the probability of making the type 1 error, we decide the likelihood of that when we set alpha. The probability of making a type 1 error is alpha. We decide that. So when we set alpha to be 5%, 0.05, we're setting the probability of making a type 1 error to be 5%, where we have incorrectly rejected a null hypothesis when we shouldn't have. So we set that. If we want to set the threshold to be higher and to reduce the probability that we would make that type 1 error, we can set it at 99%. We can set it at 99.9%. Right? We're 99.9% accurate, like those pregnancy tests. Because that's the other thing you do. You read the box. And you're like, how much did you pay for this test? Oh, you bought the cheap test. It's probably not very accurate. And you read the box and it's like 97.9% accuracy. Why are we concerned about this? Well, we don't want to say there's an effect when in fact there is no effect. We don't want to explain how the world works incorrectly. We don't want to do that. And to get outside of the social sciences, imagine a drug trial where we're telling you, hey, you're sick, this drug will help you. Take this drug. And you take it and you die anyways. Because the drug had no effect. So there's a phenomenon where we want to make sure that the drugs that we give people are effective, because if they're not, then that's time that we're wasting that they could be undergoing alternative treatments. So somebody's depressed, you give them a pill and you say, this will make you less depressed. And it doesn't. What's the worst thing that could happen? A person is depressed, they should be getting better, but they're not. What's the worst thing that could happen? They keep being depressed, but now they think, I'm supposed to be happier, and I'm not. So what's the worst thing a depressed person can do? Can kill themselves. Thank God I'm not in medicine. Like, whether or not a judge votes in a certain way because of some other thing, like, I'm not going to be killing anybody. Right. Those people doing the parking study, nobody's going to die if they get a type 1 error because people want to stay in their parking spots. But if I'm a medical researcher and I'm testing a drug and I'm trying to say that this drug will have an effect, and if it doesn't, holy, we're in trouble. So how does this happen, right? We've identified an error that could kill people, either through non-treatment. Well, I hate to say this, but sometimes you just get a weird sample. So you could draw a sample, and the sample would say, yes, for this sample, this treatment worked. Fancy college word, stochastic. Life is stochastic. There's a randomness to this. If something is stochastic, you can't control for every effect. Human beings are the perfect example of stochasticity. You are so freaking random that it drives me crazy. I don't understand you. Why can't you all behave the exact same way? It would make my job a lot easier. But I can say the same thing to two people and they go in actually opposite directions. Because there's just a randomness to us. So because type 1 error is user generated, right? We're using a sample. The only way to eliminate type 1 error is to never reject the null hypothesis. So it's abstinence. You don't want to get pregnant, never have sex at all. That's the only 100% way to avoid the type 1 error of pregnancy. Just never do it. Don't do social science. Don't try to explain the world. Don't try to explain human beings. Just go learn how to build bridges or something. Don't do social science. It's the only way to eliminate type 1 error. I guess I could get really dark and be like population control. Right? If you have a small enough population, then you don't have a sample and you have data on everything. It's rainy out. Let's go dark. Right? Population control is the answer. We need to keep society small so that we don't have type 1 error. Yeah. What can we do about type 2 error? Remember, type 2, the null hypothesis is false, but we don't find the effect in our sample. So we fail to reject the null hypothesis. Conveniently for us, that's called beta. Alpha, beta. Type 1, type 2. Alpha is the first letter of the alphabet. Beta is the second letter of the alphabet. We don't actually know what beta is because we don't know the true population values. So we don't really have anything to compare it to. But it's beta. It exists. It's a thing. It's out there. We've named it, therefore it is. You'd think alpha and beta are linked, but not so much. By increasing alpha, we don't have a reciprocal effect on beta. It doesn't quite work that way. But let's just say, because we don't know the true population values, we don't know how wrong we get it. There's a concept in statistics known as power. You might see that if you, particularly in probably psych and soc, a little bit in comm. In political science, we don't deal with the power of a test a lot. But you could hear that phrase, what's the power of this test? The power of the test is its ability to find the correct answer and avoid type 2 error. So that the statistical power is 1 minus beta. Yeah, I've seen this in comm. I've seen it in some people that do survey work will talk about the power of a test. It has to do with smaller samples is when you usually see it. But the idea is the ability of your hypothesis test to find this effect in the population when it exists. So the way that academics work, if you sit down, write a paper, and you have no findings, they're not going to publish that paper. So you've gone through all of the work for absolutely nothing. Nobody wants to read a journal article to see that something doesn't work or you can't explain how behavior happens. And because, this is the worst part, because nobody publishes those, nobody knows that it doesn't work. And so you end up with other people trying to do the same thing. And then they go through and they test it and they find that it doesn't work. And then what happens? Nobody knows. And then another researcher comes along and tests it out and finds that it doesn't work and doesn't get it published, and then nothing happens. So as academics, it's kind of frustrating because there's a lot that we know that doesn't explain it, how the world works, but there's no place to tell you that, except for the internet. And so what some faculty do now is they self-publish their null findings. So we can say, we looked at this and it didn't work. But there is no journal out there where I can send my work to and be like, the journal of no results in the courts. Like, I don't have that. I can't read the things that we've tested and failed. Usually what happens, and the way that academics works, we have like a minor league system called conferences. And so we go to the conference and then we show everybody our work and we get feedback on it. And there have been lots of times where I've gone to a conference and the person will do their presentation and they'll be like, I didn't find anything. And that's it. But I booked this plane ticket like 4 months ago, so I'm here. And everybody's just like, yeah, it happens. Happens to us. Happens to everybody. Don't worry about it. Keep trying. And then you try to sort of say, okay, well, here's what you should do, right? Try to do this, try to do that, try to salvage your project. Maybe if you thought about it this way, or have you considered adding this variable? Try to reclaim it. But the problem is we don't know what has failed. We only ever publish the works that show this is an effect. So we've got a knowledge sort of hole. Like, and we just throw stuff away into the no finding hole, and it just goes away forever until the next person does it, and then they come up and offer their sacrifice to the knowledge hole. How does this happen? Well, again, chance. You got a bad sample. You went to the wrong spot to look. You should have found this. You know, how do you not see this? It's like giving directions to somebody, and you're like, turn left at the McDonald's, and they're going, there is no McDonald's. It's like, no, really, turn left. I don't see it. I swear it's like my kids. Like, John, put your shoes on. I don't see shoes. Well, they're right there. Where? The place that I'm pointing? Yeah, I can't see that. Open your damn eyes, fool. They're right there. Nope. No. Oh, these. Yes. God damn it. The green things on the floor. Put them on your feet. Oh, okay. It's just a communication issue. Or the effects could actually be really small and difficult to detect, right? And again, speaking to this idea of power, how well can we see differences? Well, if the differences are really small, some people might not see them. Their eyesight could be bad. They might not be able to tell the difference. It's sort of like ability to see color. Do you know a person that can't see color? I mean, there are actual colorblind, or I guess color difficult people. But, you know, is this blue or black? I'm not wearing my kind of green pants today, but, right? There's just some people that can't really tell the difference. Is this gray or beige? It's grayish. Colors are tricky. Small differences. You could also have issues with your research design. You could be looking at the actual wrong sample. You could be measuring something incorrectly, and therefore you don't find the effect. When you take a variable and you recode it, you lose some of the differences. So you can take a variable that is continuous, like temperature. Temperature is something that could be really, really precise, because even the thermometers we stick in you are like 98.6. Well, we could get even more specific in that if we had the correct instrumentation. We could keep going in digits. And then you come along and you're like, I know we've got this temperature data, but let's just do hot and cold. Or you could take something that actually makes sense, like temperature data, and recode it as fever. If it's above 98.6, it's in the fever category. If it's below 98.6, it's in the, you're okay category. So we could actually wreck our data by recoding it incorrectly. Take the variation away. Because I'm pretty sure when it comes to fever or not, there's a difference between like 99 and 110. By the way, if you ever have a fever of 110, you're dead. You've become a zombie. You're no longer alive. Your brain has been cooked. So our 4 boxes, back to them. We now know what alpha and beta are. Alpha is our type 1 error. We control the probability of a type 1 error. by where we set alpha. And like I said, the convention in the social sciences is 95%. We're okay being wrong 1 time out of 20. Those are good odds. Type 2 error is we miss it. We're actually okay between type 1 error and type 2 error. Type 1 error is describing the world wrong, and type 2 error is not yet describing how the world works. We'll get there eventually, either through a different sample or better data, maybe a more precise measurement, a new method perhaps. We'll get there eventually because we're going to keep making the same mistake over and over and over and over and over again. We have to, because I have to publish. So eventually I'll find something. I'll find this effect where nobody else has found it before. This presence of alpha in type 1 error is also why in the textbook, Howard, every time he does a hypothesis test, he always tries to find, okay, what level of significance is this? Me, all I care about is if it's significant or not. If it's significant, great. I can show it to other people and try to get it published. But for him, he's sort of saying, okay, we need to know what the level of significance is because it tells us what the probability of making a type 1 error is. Because there are people who want to know that. You want to know that. I know that because that's why they put it on the back of the pregnancy test box. Because you read it and you're like, oh, woo, you actually might be pregnant. Yeah, 97.9%. So, some strategies. Right? If we want to control type 1 error, what can we do? Well, we can have a higher standard. We can make it harder to reject the null hypothesis. If it's really an effect, it should be a big effect. We shouldn't just be like, ooh, 1.97, yay! We just made it over the edge. We also should see the effect in repeated samples. The only problem is that if we think about it, if we decrease type 1 error, we might actually accidentally increase the probability of making a type 2 error. By a little bit. Because then we're not rejecting something that we could have. Mathematically, alpha and beta aren't in the same equation. But theoretically, as we think about, okay, if we're going to mitigate alpha, in the end, what we could do is we could do it in a way that would increase beta. Might not, but it's possible. Right? We could miss this effect that actually exists. The only way to mitigate against the type 2 error is to make it more likely to reject the null hypothesis. Of course, when we do that, what will happen? If we increase the likelihood that we'll reject the null hypothesis, we'll also increase what? The probability that we make a type 1 error. So if we make it easier on ourselves, so you could increase the sample size. And I've shown you how that n being in the denominator of the standard error works. You increase n, you lower the standard error, you lower the denominator, your t or your z-score gets bigger, and therefore makes it more likely to reject. So you could increase your sample size. Larger sample size, lower critical values. All right, looking at that t-table, if you have a degree of freedom of 1, your critical value is like 12. But as we go down the column, eventually we get down to 1.96. You could raise alpha. However, we already discussed that would raise your type 1 error. Another thing you could do is use a directional hypothesis. And I'm guilty of doing this. I've done this before. A directional alternative hypothesis says you take the 5% and you put it in one of the tails. And that's it. So let's say you put all that 5% in the positive tail. I think your 1.96 becomes like 1.68. And that becomes your new critical value. Because we've added the 2.5% over here. It's all right here. So we've gone this way. We've lowered our critical value. But you only get to use one side. So if you do this test and you get a z-score of -10, you still don't reject the null hypothesis. Well, actually, you furiously delete that section you just wrote, and you abandon the one-tail test, and you go back to the two-tail test. And then you rewrite the front of your paper to have the opposite result that you thought you were going to have. Science. Got to publish. Oh, well, an examination of my data led me to rethink the causal mechanism behind blah, 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 blah. I got this. I can do that. Here's how it is. Well, in theory, we would think that increased public support of minority groups would lead to a corresponding move by judges to grant rights to said minority group. But in fact, increasing public opinion towards the minority group leads to a backlash, and the judges, as a counter-majoritarian institution, actually require that the political processes make the change instead of them making the change themselves. So therefore, they are less likely to vote to grant rights to a minority group. Ta-da! See what I did there? I just completely reversed it and explained the negative outcome that I didn't think would happen. Actually, I'm right. They actually do. Judges follow public opinion, by the way. There is no backlash. But I was ready. I could explain it both ways. We could change our sample. We could increase the between group variability. So we try to use more of the differences. This is hard to do if your difference is binary, like men and women. But if you're looking at, say, income and the effect that income has on voting, instead of just having lots of people in the middle, you could spread your sample out and get people at both ends of the full spectrum. Same thing with education. You could try to expand that out. And in fact, one of the general social survey questions asks, I think it's EDUC, asks the number of years that you attended school. Not just what degrees you have, but the actual number of years. And when you look at that, you'll be kind of surprised that there's some people in the single digits. Like, dude couldn't make it out of elementary school. Sample size is the big one. How we deal with N makes big changes. And again, you will experience this. If you have a variable that has 64,000 responses, I'm telling you, everything's going to be statistically significant. You need to sort of pare that down a little bit. The bigger the sample size, the more likely we are to reject the null hypothesis. It decreases that standard error. However, we want large sample sizes because we want to be more confident in our conclusions. We want our sample means to be closer to the actual mean. And one way to do that is to have larger samples. So we're in a situation where you want a large sample so that your sample mean is close to your population mean, but if your sample size is too large, then you sort of rigged the math. And the advantage is in your large sample size. It is meant to be this difficult. What we can do is we can think of our sample size relative to our variance. And so there are some ways to look at the differences within your sample and how much difference there is. In some instances, we actually don't measure your actual data. We measure you relative to something else. So in political science, we have this thing called the Gini coefficient, G-I-N-I. The Gini coefficient is something that we use to measure income, but we do it in a way that measures your income relative to the society you live in. So if we were just to go around and measure how much money you make in country 1, country 2, country 3, country 4, we would notice that there are massive differences. And that the poorest American with his, I don't know, $12,000 yearly income would probably be a solidly middle-class Jamaican with a $12,000 a year income. Jamaican money's awesome. It's $125 is $1 US. So you go to the ATM and you take out like $80,000. Awesome. It's really cool. So sometimes instead of trying to explain the effect of income, we try to measure the variance instead, right? And that's the Gini coefficient. And it allows you to compare income inequality not only across time, but also across spaces. I don't want to do this. I'll show you this one. There's this thing out there called Cohen's d. And to link back to an earlier study, we want to know what the effect of the two differences are. So remember with the parking lot study, we found that there was a statistically significant difference. It was 9 seconds in our sample, and we said that's a big enough difference in our sample to say that there is one in the population. But if you look at that difference of 9 seconds when compared to the amount of variation, is it still a lot of difference between the two groups? So again, we're taking the difference that we observe relative to the variance that we observe as another way to sort of to examine whether or not, I don't want to say that we were correct, but how much of an effect that difference is. So Cohen's d is equal to 2 times t. T is the actual statistic that we computed back in that example. So when we arrived at a t-score and we looked at that relative to the critical value, that's the t. Divided by the square root of the degrees of freedom. So we have in here a proxy for sample size. So 2 times the result that we got, which was 2.42. I believe the critical value for that one was like 2.048 when we did that one. So that was a statistically significant finding. So the actual 2.42 divided by the square root of 28, because there were 15 on each side. And we had 2 groups, so n minus k, n minus 2. We get a d of 0.91. What does that mean? Are we happy? Are we sad? Well, what Cohen's d does is it tells us the magnitude of the effect. It's going to range most likely between 0 and 1. A small effect we would get at a 0.2, a medium effect at 0.5, and the large effect is 0.8 or higher. So you can tell this is a very precise test. Yeah?
If it equals less than 0.2, is there no difference?
We would say that although it's statistically significant, the effect itself is small. And that's why I don't like how Howard leaves out that word statistically significant, because if I say this has a significant effect, I think sometimes people are thinking this, like the magnitude or the size of the effect. A statistically significant effect just tells me that we believe our sample is not 0. This is telling us we believe it's not 0, and the fact that it, relative to the sample size and what we sort of got, that's probably 9 seconds is a large effect, even though it's just 9 seconds. Okay. The reason that it's good to do this, particularly if you have a really, really large sample, is I have seen differences. So I've seen papers where students did the difference of proportion between men and women, and it was like the difference was actually less than 2%. So men are 54% and women are 52%. And that came out as statistically significant. And you're like, holy, that's a really small difference. And you're saying you observed the small difference in a sample, and you're going to reject the null hypothesis that men and women are the same based upon this small difference in the sample. Well, yeah, because they had 62,000 observations. Any difference is going to come back as statistically significant. The next step is to say, okay, given the variation between those two proportions, and we saw 0.02, is that a big variation? And the answer is most likely going to be, well, no. Because the t-value was not that big. So anyways. So this is an option. There are other similar tests out there. You don't see these as much when you're reading research. Okay. So that was our discussion on hypothesis testing. And again, the main reason to do this is because when you're writing up your results, I want you to sort of be aware that you could still be wrong. It's a possibility. And that's why we sometimes report the actual probability value. When I write a paper and I'm reporting the probability of my sample, I'm reporting the exact number. And I want to say how small alpha actually is. Okay, I've left some time at the end because I want to go over the paper again. And I want to sort of have this be a little bit more interactive. So I'm going to stop the record. Well, I'll leave the recording on, but I'll probably have to repeat myself so that the people who aren't here can know what we were up to. So remember last time we talked about the paper, I told you I want you to use the SDA website. So let's go ahead and bring that up. Come on, Internet, you can do it. I think it's called eduk. Let me see if that is in fact true. Yeah. What's the highest grade in elementary school or high school that you finished and got credit for? 165 people, 0. I don't even know what to do with that. They never went to school? maybe they're homeschooled. I don't know what to do with that. Also, I'm curious who went to 20th grade. Maybe they just kept adding on the years of college, right? Because you can see a lot of people just were 12 and done. Maybe maybe they were the kindergartners. I don't know. Because technically you do 13 grades in school, right? K through 12. There's K1. I don't care enough to actually read in the code book, but I do like looking at this and be like, this is another way to measure education, right? So has anybody played with this and run into any issues? None of you have started work on your paper yet, have you? No, not a single one of you. Has anybody thought about what they were interested in? Yeah, what you got?
Like, are women more prone to, like, favor gun control?
Yeah, okay. So did you find a gun control question?
Yeah, but I don't remember where, because I was just messing around.
Okay. So again, I like the General Social Survey because it gives me variable names that I can remember. But anytime I would look at this, I would also go and compare this to the American National Election Study. I've yet to have a student write a paper where they use two different data sets and they compare if the results are different and from one data set or to the next. That'd be shiny. You guys could do that if you'd like. Have you ever... Oh, I got to look at this one. This is gun. Have you ever been threatened with a gun or shot at? I love this question. This is one of my new favorite questions. Have I ever been threatened with a gun or shot at? Would it count if I had a cop put a gun in my face? Yes. I can answer yes to this one. Albany City police officer rounded the corner, put a shotgun in my face because he thought that the television that we threw off the roof of the house was a shotgun. Because old TVs had these things in them called picture tubes, and they're vacuumed and they're pressurized, and when they smash, they go pop, and the neighbors called the cops. So I've had a shotgun in my face. Yay, college. It was the 90s. We did things differently than you all do them today. You can't have that experience because we didn't have social media. So yes, I get to answer this one. Have you ever been threatened with a gun or shot at? 20% of people have been threatened with a gun or shot at, which could be a veteran, could be somebody that has served in the military and been in a firefight. They've been shot at, or they've been aimed at. Sure. So there's lots of possibilities with this question. I like this one. I wonder if this would influence your thoughts on gun control. I wonder if knowing somebody that's been murdered, I think that's in here too, might influence your thoughts on gun control. I'm not saying the gender one's not fun, it's easy, but let's take a second step, right? Let's see what else is out there. Oh, I was hoping this was something else. I was hoping this was, have you ever been questioned as a murder suspect? It wasn't. I don't know. Because there's a lot of these questions of the person the murder victim close to you, but haven't found the actual one. But if you're interested in the death penalty, here's cap pun. Do you favor or oppose the death penalty for persons convicted of murder? Favor or oppose? Again, if you're going to pull this data out, you need to recode it as a binary. And a dummy variable would have favor be 1 and oppose be 0. If you calculate the mean of your zeros and ones between the two groups, you actually end up with a proportion. Okay. The other thing to remember, so let's do a crosstab. Remember that when you're trying to find a pair of independent and dependent variables, you have to check to make sure that they are in the same year. And so if you ever run a crosstab and it tells you there's no results, it's not because you typed in the wrong variable name. It just could be that your questions aren't asked in the same year. So use that year variable. I did. Yours is in my folder. Yep. Yeah.
What do row and column tell you? Like, which one do you type where?
Okay, so I always think about how I want the data to be viewed. So the columns are the up-downs, like a column on a house. And what happens if I do the year as a column? Going to look really ugly. So the first thing I asked myself is, how do I want to look at this? This is ugly. This will go off the page. It just keeps going and going and going off the page. If you're trying to set this up in terms of an independent and dependent variable, I think it's, well, I'll have to take a second look. It would be, the rows are the independent variables and the columns are the dependent variables. Yes. So if you're doing like a crosstab, you would want to put the dependent variables up top and the independent variables on the rows, I think. Yeah, I'll double check that. I don't do that a lot. Usually we do them, if we're doing a graph, it's actually the independent variables on the bottom and the dependent variables over here. If you are going to have the SDA website sort of make a table for you, remember you have to turn the weights off. And then you have to make sure that you look through these options. So are you going to do the percentages within the column or within the row? Something like that. Or you could just leave them out and just get the raw numbers. Take the weights off. You can turn the colors off too. The colors are the computer sort of doing a z-score on its own. But you haven't told it how you want it to do it. So you probably should turn the colors off. But this gives you the raw numbers. Again, this is backwards, but. So next week when we do class, I'm going to teach you something called a chi-square. And a chi-square is when you have that crosstab table and you're comparing two dependent variables that are both categorical in nature. So the one example has 3 colors. If you were doing a paper about political parties, you could have different political parties. We can treat race as between, however you want to construct it. White, black, other. or we could separate out all the various things we call Asian, because I'm sure Korean people and Japanese people consider themselves the same, right? They don't. So I'm going to teach you that, and you can actually use this to generate your data table and then compute the chi-square using the table that you're given here. That's an option. Any other questions about finding data for your papers? I've got 15 more minutes. Just for you. Yeah?
Did you say we are allowed to use variables from two different data sets?
No.
Okay.
So the way that data works, if it's in a data set, it has to have the corresponding information with it,
Figured as much.
right? What I said earlier was, I think it would be neat to see if which data set you use matters. So if you're doing something just like the capital punishment one, I'm pretty sure the American National Election Studies has a capital punishment variable. Let's take a look. So the ANES, this is for all of the questions from 48 to 16. They don't ask this every year because they focus on elections, so you're more likely to get this in even number years with federal elections. Okay. Wow. Death. Okay, I don't believe that. Yeah, but I'm searching the term. I'm not searching the name. Okay. Economic policy, war, rights of the accused, cooperation with Russia, defense spending. Like, it's got to be in here somewhere. Wow. Well, that looks stupid. I mean, they even got food stamps. How do they not have capital punishment? I mean, they've got an ERA question. Should women stay out of politics? Segregation. I wonder. Let me try one more thing. I wonder if it's because I've got the aggregate. Let's look at a single year. Yeah, here we go. So here's a single year. This is the 2016 American National Election Study. Does the respondent favor or oppose the death penalty? 161233. So you could look at this and compare it to CapPun and see if the two surveys produced a different result. Why? Just because I think it's neat. And you could show off. One of the things that we do say is that when you find the same result in different samples, then that sort of has a cumulative effect of saying, yeah, this actually does have an effect. So when you hit that 8th pregnancy test and you're like, oh, okay, I think I'm pregnant, yeah, if you go through 8 different surveys and you get consistent results, and whatever difference there is in survey methodology and where they got their sample from, you would say, yeah, we're pretty confident. We found this thing 8 times. It's called replication. Replicate previous findings. I guess that's another trick, is that when you're using the American National Election Studies, you might want to look at just one of the years instead of the combined file. Although looking at some of the old ones, again, really cool data. I think it's this one. I didn't find it, but I know that in one of these 2 surveys, they measured race as skin tone. And so on a 1 to 10 scale, what is your complexion? Here's a different one I found. If the respondent is black, what's their skin color? Very dark brown, medium brown, light brown, or very light brown. That's a different way of thinking about race. Man, I know it's in here. Maybe it's tone. This one doesn't like me today. It's in one of them. I'll have to find it. Again, another reason to compare the 2 is that they might ask the question in a slightly different way, one that's better for what you're trying to do, or does how we ask the question matter? Something to look at. Your papers are really up to you. You can do the bare minimum and just be like, I tested this thing, it's significant, I'm done. And it's like, okay, you did it right, I think. Here's your C, congratulations. You passed. I mean, we can do that. If you just want to do that, you can. But I'd really like you to, do something interesting. That's a warning. Bare minimum gets you your C. Anything else? Okay. Remember, I won't be here on Thursday.